mirror lenses for cameras. So last year I've spent... Hey everyone! Today I want to take a closer look at mirror lenses for cameras. So last year I've spent quite a lot of time on designing and making a compact monolithic telescope. And this item was made of a single piece of glass and it has a long focal length compared to its size. In this video I will discuss a few conventional mirror lenses which have quite similar designs and also have a relatively long focal length for their size because of a folded optical path. These lenses can be found online quite abundantly and be bought for relatively little money. So in this video I'll take a detailed look at the optical performance of this type of lens, and in an upcoming video I will show you how they are constructed and if they can maybe be tweaked to perform a little better. In this video I'll have a look at three lenses. The 800mm focal length Vivitar Series 1 lens, which is of fairly recent production date, a 600mm Sigma mirror telephoto lens, probably from the 1980s, and a 500mm Solicore lens, which is probably also from the 1980s. I bought these second-hand with prices varying between 50 and 100 euros. The first lens I got in was this Vivitar 800mm focal distance lens. It has an aperture of approximately 100mm, making it an f8. It also has a large central obstruction that is about 47mm in diameter. The lens looked brand new and unused and had clean and very clear optical coatings. It came in a box with a pouch and even a lifelong warranty. No serial number though, but I was pretty excited to take a peek through this high definition lens. So I mounted it on a Canon 90D using a T-mount adapter and just pointed it out the window. Now my initial excitement disappeared in just a few seconds, because it was immediately clear that this lens, despite it being in excellent cosmetic condition, wasn't sharp at all. Images remained fuzzy, no matter how hard I tried to focus, and I must admit that never before had I seen a commercial lens perform so poorly. Just to give you a frame of reference, when you compare the sharpness of this lens to a conventional 400mm telephoto lens, you can clearly see a huge difference. Even though the conventional lens has half the focal distance, it outperforms the 800mm Vivitar lens on sharpness by far. But in fact, you don't even need a high-power telelens to do this. Even a simple 135mm focal distance lens, which I bought in a thrift shop for about 10 euros, reproduced more detail when you zoom digitally into the images. Now my initial reaction was that the mirror lens was probably a bad apple in a batch, because I remembered the Vivitar brand and especially the Series 1 indication to be generally of good quality. So I did a search online about the experiences of others, and it turned out that this lack of sharpness is actually very common with this particular lens, leading to quite a lot of disappointed buyers. Okay, so maybe I should have done a little research before actually buying this lens. In fact, it seems to be a far departure from the original Vivitar Series 1 mirror lens, which was of good quality. The original lens was actually called a solid catadioptric. That name is actually kind of misleading because it suggests that the optics are made of a single solid piece of glass, which is not the case. It actually contains 7 individual optical elements. Anyway, it turns out that the company behind the Vivitar products is not the same as the one back then. The Vivitar brand was registered by Ponder and Best Incorporated in the early 1960s, and in general this company rebranded Japanese and German products under the Vivitar name. Now, after the founders of the company died, the brand knew various other owners, and in 2006 Vivitar was bought by Syntax Brilliant, a consumer electronics manufacturer. Unfortunately though, they went bankrupt in 2008. At that point, a company called Sucker International acquired the brand name and intellectual property and continued to sell products under the Vivitar name. But these products were now made in China and Korea, and apparently they're on a different quality level than the Vivitar products previously manufactured in Japan and Germany. Now I guess there will always be quality differences between companies and products, but if there's one thing I really hate, it's when companies put products on the market whose quality is so bad that they're basically unusable because you cannot make a single decent picture with this lens. So the best thing you can do is turn it into a nice plant pot or maybe a funny hat. Anyway, this lens was kind of a disappointment. But luckily, a few days later, a box arrived with a different lens, the 600mm Sigma mirror telephoto. Contrary to the previous lens, this one is quite vintage. It was first introduced in 1979 and I estimate this lens to be between 30 and 40 years old. Cosmetically, the Sigma lens looked okay on the outside, but as for the optics themselves, they were not in too good a state. Inside, fungus and various damages to the coating were clearly visible, indicating that at some point in the past, condensation had taken place inside the lens. Also, the coating looked kind of yellowish, probably due to oxidation or even nicotine. So after these initial discoveries, I was afraid that I was in for another disappointment. But what do you know? This lens turned out to have much better image quality, despite all the fungus and bad coating. Here you see a comparison where I zoomed in on details in the images of the Sigma and the Vivitar lens. It's quite a difference, right? So obviously, the flaws in the reflective coatings of this lens do not have much of a negative influence on the optical quality. I must admit though that in general I did not find the images of mirror lenses particularly pleasing, especially the circular shape of the bokeh. And if you search online, this is actually one of the most frequently mentioned drawbacks of catadioptric camera lenses, the unnatural looking out of focus effect due to the central obstruction in the lens. For proximity photography, this effect will always be an issue. However, if you were to use this lens for astronomy, this would not really be a problem because basically everything is at infinity.
من ساعة ما اشتريت التنين ده وهو ما بيطلعش نار خالص. بالصدفة في مرة في الفرج على التلفزيون فجأة حصلت حاجة غريبة جدا. التنين أخد من كيس دوريتوس الحريف الجديد.
So when evening came, I pointed this lens up to the sky, and with a full moon and a lot of light pollution, the only other things I could see were basically particularly pleasing, especially the circular shape of the bokeh. And if you search online, this is actually one of the most frequently mentioned drawbacks of catadioptric camera lenses, the unnatural looking out of focus effect due to the central obstruction in the lens. Much better image quality, despite all the fungus and bad coating. Here you see a comparison where I zoomed in on details in the images of the Sigma and the Vivitar lens. It's quite a difference, right? So obviously, the flaws in the reflective coatings of this lens do not have much of a negative influence on the optical quality. I must admit though that in general I did not find the images of mirror lenses particularly pleasing, especially the circular shape of the bokeh. And if you search online, this is actually one of the most frequently mentioned drawbacks of catadioptric camera lenses, the unnatural looking out of focus effect due to the central obstruction in the lens. For proximity photography, this effect will always be an issue. However, if you were to use this lens for astronomy, this would not really be a problem because basically everything is at infinity. So when evening came, I pointed this lens up to the sky, and with a full moon and a lot of light pollution, the only other things I could see were basically the planets Jupiter and Saturn. Thing is that the 600mm focal distance is actually kind of limited if you want to see planetary details. This is because the projected size of the planets on the camera chip of the Canon 90D are too small to show a lot of detail. Still, they're somewhat recognizable. So I guess this lens is nice if you stick to an occasional look at the moon or maybe at some deep sky object. However, I would not recommend this type of lens for viewing small objects like planets, mainly because of the limited magnification. As a bonus, I bought this little Soligor mirror lens with a focal length of only 500mm, so the shortest focal length of all three mirror lenses. It came in the original 1980s style box with a lens hood. Cosmetically it looked fine, also the coatings on the inside, but as with the Vivitar lens it displayed a significant fuzziness, although not as bad. And while testing, I noticed that it had these asymmetric out-of-focus ring patterns, even in the center of the image field. And this indicated that something inside was not positioned correctly with respect to the optical axis. So I'll put this lens aside for now, but in the next video I'm going to address this particular problem. So to summarize the previous in one sentence, I bought 3 lenses, named blurry, moldy and squinty. After I had checked out the first Vivitar lens, I considered whether it would be possible to improve the performance by making a small change to one of the optical surfaces. And since the lens was a total failure anyway, I thought it was worth a try. But before I could do this, I first wanted to see what the problem with the optical performance was. Now, there are many different ways that you can measure optical performance. For example, you can take a high resolution test chart and look at how the patterns are reproduced in the image by the lens, and then put this as a result in a graph. And this gives you a measure of optical performance. But by itself, this test does not give you any information about which aberration in the lens is responsible for image errors or how to correct them. So in order to measure this particular aspect, I decided to evaluate the lens using interferometry in an autocollimation configuration. And because you might not be familiar with this particular method, let me briefly discuss how this works using a few schematics. For interferometry, we generally use well-collimated parallel beams of coherent light. And in autocollimation, this is also the case, but here we use a collimated beam of light which is generated by the optic under investigation itself. So assume that you have a nice point-like source of light on the imaging side of the lens and you have a very good optic. Then basically this light will exit the optic in a well-collimated beam. If we now place a mirror in front of the lens that directs the light back in the reverse direction, this light will be imaged back into a very small spot. However, if the optic is not perfect, then first, it will not leave the lens perfectly collimated, but second, on the way back, it will encounter the same aberrations again, and this will result in a much larger focal spot. Now, of course, this is not all, because we need a quantitative way to measure the nature of the aberrations, and we can do this by using interferometry. In this case, we take a coherent light source, like a laser diode. We focus the beam tightly into a very small spot, and from this we create a divergent beam of light. We then use a beam splitter to split this beam into 2 parts. One part is used to create a reference wavefront, and this is directed into a spherical mirror, which basically focuses the light back into a very small point on this side. And after the light has passed the focal point, this wavefront is nicely spherical. Now, the other fraction of the light goes into the optical system under test, which is in autocollimation, and also returns the light to that same point. But this wavefront now contains information about the aberrations of the lens, and so by evaluating the interference pattern between the 2 different wavefronts, we can calculate the errors present in the lens. And in this way we can measure the wavefront error and identify the problems in the optic. And of course, this setup is not only useful for mirror lenses, but can in theory be used for any confocal lens. Now, this setup does not really look very complicated, right? But in practice, it's not that easy to accurately perform this type of experiment for various reasons. You need quite a lot of high quality gear, like a fairly good beam splitter, a high grade confocal lens, a good spherical reference mirror, and an optical flat of sufficient size. And on top of that, you need tools to accurately place and orient the different components correctly to achieve a good alignment between interferometer, lens, and optical flat. So let me show you the actual setup that I built and explain a few things. Here is the coherent light source, a red laser diode, which is on an aluminum platform, together with a gradient index lens, the beam splitter, and the spherical reference mirror. And this creates a spherical wavefront in the direction of the camera. And by the way, to validate the quality of this part of the setup, I referenced it to several very high quality spherical Perkin-Elmer wafer stepper mirrors. For those of you interested, here you see the calibration measurement showing that the interferometer part has sufficient accuracy to do measurements with. Next, we want to use this this setup to measure a lens in autocollimation, and the lens is mounted in this contraption, which allows for the manipulation of angle and position over a total of 6 degrees of freedom. This lens manipulator is pretty vintage. I saved it from the trash bin a few years ago, and I've used it on quite a few occasions because it's a very versatile instrument. Now, on the other side of the lens under test, I placed a large optically flat mirror, which is a Zygo zero-dur dichroic mirror, also bought on eBay. And although the reflectivity at the laser wavelength is only 50%, it's a very good large diameter optical flat. On this side of the setup, we can now record the interference pattern with a camera. And based on the recorded images, we can create a wavefront map using the open source software DFT Fringe. I've discussed this process in earlier videos in some detail, and I will put links in the description in case you want to download the software or want to know how to use it.
طابور طويل.
Links in the description in case you want to download the software or want to know how to use it. To check up if the setup is working, I first tried a few other lenses. High quality spherical Birken-Elmer wafer stepper mirrors. And for those of you interested, here you see the calibration measurement showing that the interferometer part has sufficient accuracy to do measurements with. Next, we want to use this setup to measure a lens in autocollimation, and the lens is mounted in this contraption, which allows for the manipulation of angle and position over a total of 6 degrees of freedom. This lens manipulator is pretty vintage. I saved it from the trash bin a few years ago, and I've used it on quite a few occasions because it's a very versatile instrument. Now, on the other side of the lens under test, I placed a large optically flat mirror, which is a Zygo zero-dur dichroic mirror, also bought on eBay. And although the reflectivity at the laser wavelength is only 50%, it's a very good large diameter optical flat. On this side of the setup, we can now record the interference pattern with a camera. And based on the recorded images, we can create a wavefront map using the open source software DFT Fringe. I've discussed this process in earlier videos in some detail, and I will put links in the description in case you want to download the software or want to know how to use it. To check up if the setup is working, I first tried a few other lenses, like the conventional 400mm Panacore lens previously used in the visual comparison. Using the interference patterns recorded with this lens, you can calculate the wavefront error. And it turns out that the measurement mainly shows a spherical aberration, which you can identify by the bump in the center. We also observe this peculiar type of astigmatism, which shows up as variations in the wavefront error as a function of the angle with respect to the center. This type of aberration is called trefoil astigmatism. Now, trefoil is frequently caused by mechanical stress, for example by fixation screws, which in a lot of optics are placed under a 120 degrees angle with respect to each other. And when too tightly fastened, they can result in the deformation of an optical component, which can then cause this type of wavefront error. So the trefoil wavefront error indicates that there might be a stress-related issue somewhere in this lens with a mechanical cause. So given the presence of these two main aberrations, how do they influence optical performance? Well, as said before, there are many ways to define this property. But for this video, I just wanted to use something simple that can be represented by a single number. I chose the Strehl ratio because it touches upon the essence of what a good optic should actually be doing. Okay, so what is Strehl ratio? Well, say we have this perfect lens, which, for example, is focusing light from a point source at infinity into the smallest spot possible. As you can see here, the light is not focused into a single point, but is a spot of a certain size with some rings around it. And this is because of the wave character of light. And this smallest spot possible is also called the airy disk. If you make a cross section of the spot and plot intensity versus position, we get this kind of curve. Let's say that the spot is centrosymmetric and that this curve represents the light distribution imaged by the lens. Now say that we have a less than perfect lens that gives us a somewhat different intensity pattern. This means that some of the light ends up in the wrong places. Now say we have normalized these curves such that the area under both curves is the same. For this situation, the Strehl ratio simply represents the fraction of the light that ends up where it should have, if the lens were perfect. So basically, if we take the curve of the perfect optic, we overlap it with the imperfect one, the Strehl ratio is defined by the fraction of the area that is located under both curves. So what this means is that if the Strehl ratio of an optic is 0, then light ends up everywhere but where you actually want it to end up. And if the Strehl ratio is 1, then the optic is perfect because both curves are identical. And so every value between 1 and 0 specifies a certain degree of optical imperfection. For the 400mm telephoto lens test, our software calculated the Strehl ratio to be around 0.38. And even though this indicates that it's not perfect, it's not as bad as you might think. Anyway, now that we know that the setup is working, let's measure the wavefront error and Strehl ratio of the Vivitar lens. And here is the result of that measurement. It shows us that indeed this is one really bad lens. For starters, the Strehl ratio is calculated to be 0, which means that virtually all of the light ends up in the image plane where it was not supposed to go. Now, I know this sounds kind of funny because you still see an image when you look through it, but it explains the extreme fuzziness of this lens. The light distribution would actually look something like this, which is a far departure from the ideal airy disk. And the main cause is a large spherical aberration, which is in the order of 1.5 lambda RMS and about 4 lambda peak to valley. It's also got quite a lot of astigmatism in the X and Y direction, and this suggests deformation or misalignment of one of the optical components inside. And the value of the wavefront error could certainly explain why we get such unsharp images with this lens. Now let's quickly compare this to the 600mm Sigma lens, which demonstrated much better optical performance. Here is the result of the Vivitar lens again for reference, and here is the identical wavefront error measured on the Sigma lens. I deliberately put these two wavefront plots on the same z-scale, so they're easier to compare. But what you see is that the Strehl ratio of the Sigma lens is only around 0.12, which is not that great at all, but is of course a huge improvement over the 0 value of the Vivitar lens. Also, the RMS wavefront error is 0.23 lambda, 7 times smaller than the value of the Vivitar lens. And if you look at these two measurements of the wavefront error, the huge difference in the image quality between the two lenses is not really surprising. Now, before you say that the Sigma lens apparently is not a very good lens either, please keep in mind that the designs of lenses for photography always contain a lot of compromises. So contrary to the monochromatic laser light that we used in this experiment, the photography lens has to deal with multiple wavelengths. So we want the different colors originating from a white light object to end up together in one spot, and of course we want this property in the complete image field. Also, we want as little image deformation as possible, and on top of that we want the lens to produce acceptable images over its complete focusing range. In some cases, we even require planar projection properties of a lens. So what I mean to say is that image sharpness is not just about measuring a Strehl ratio on the optical axis using monochromatic light. It is determined by many other parameters, and the measurement method presented here is just a way to determine which aberrations are present given a specific optical configuration and wavelength. Okay, so now that we've identified the main problem with the Vivitar lens, It might be possible to find ways to improve the optical performance a bit, but this is actually quite an elaborate process. So in a follow-up video, we're first going to take a look at what's inside the mirror lenses and discover how they work. And I'll try to improve the sharpness of the Vivitar lens a bit by modifying one of the two reflective surfaces inside. In addition, I will show you how I gave Mr. Squinty, the Solicore mirror lens, his razor sharp eyesight back. So, till next time.